My name is Marija Ivković and I'm hydrologist at Republic Hydro-meteorological Service of Serbia, and I will present you the last model today. It is also one of the distributed version of hydrological models that will be available very soon to be run through the portal. Now, some of the activities are completed, but HBV is not available through the portal. So very soon you will have the possibility to run it through the portal. HBV is a continuous rainfall runoff model, meaning that it can generate runoff when you force it with rainfall. For the DRIHM project, we choose the version with hourly time step, but if you run the standalone version, you can choose any time step that you find appropriate for your problem. As Professor Luis mentioned, the phases that are describing one hydrological model, in HBV we have a snow routine, we have interception routine, soil routine, and finally the runoff response routine. This is the first routine, and here is where the precipitation enters the model. Depending on the air temperature, the precipitation will be divided to the snow or to the rain. So if the air temperature is below user-defined value, threshold value, the snow will be, the precipitation will be recognized as snow. Otherwise, it will be recognized as rain. If the precipitation is snow, it will be added to the snowpack. Otherwise, it will be added to the liquid content, water content in the snowpack. There is also one interval within which we have something that is partially snow, partially rain. So we have a sleet, and water content in snow is not unlimited. So if it is exceeded, the surplus water will be available for the infiltration. So on the part of the catchments where we have vegetation, not all of the precipitation will end immediately on the ground. So part of the precipitation will be temporarily stored on the canopy, and it will be slowly released to the ground or will evaporate to the atmosphere. So this process in HBV is represented with maximum interception storage, and it can be set for every grid cell according to the land use. So the interception storage is filled with the water that is coming from the snow routine. Any surplus water will be available for the infiltration. And if we have evaporation from the interception, it will be subtracted from the potential evapotranspiration. The next process is evapotranspiration. That is one of the major processes of the hydrological cycle. So you probably know that evapotranspiration means evaporation plus transpiration. Evaporation is water that is converted to the vapor from the soil or from the water surfaces, and the transpiration is vapor that is produced by metabolic activities of the plant. So those two processes are modeled on this way. So we can say that evapotranspiration will increase as the soil moisture increases. But it will not increase indefinitely, so we need to push a limit that is one predefined value, after which the evapotranspiration becomes equal to the potential evapotranspiration. This is a very simple but efficient method. So the next phase is soil routine. This represents the soil. And it is modeled that the water that is coming from the snow routine and water from the interception routine is now ready for the infiltration. But in the soil, it is defined that soil have a limited liquid water content. So if we have more water, it will go out as direct runoff. The other part of the water will go to, will infiltrate and partially will stay in the soil as soil moisture. And after that, it will go out as a seepage water. So this is the function that defines what portion of the incoming water will stay in the soil as a soil moisture and which part will go as a seepage water. When you look at any flood wave there, you will probably not notice that this consists of two components. The first component is the runoff that is a quick response runoff, and one slower part is the base flow. Those two waves that are composing this one are shifted in time, so it was very important to make lines that will generate those two different processes. So in HBV, it was solved with two linear reservoirs. The first one, the upper one, is generating the quick runoff, and the second one is generating the base flow. Those two reservoirs are connected with the process of percolation, and the upper reservoir and soil are connected with process of capillary flow. Now, if we look the shape of one upper stream hydrograph and the one that is registered downstream, we will see that those two waves are different in shape because you have a process of translation and also the process of the attenuation. In the HBV, this transformation is solved using the kinematic wave method, and this method is a simplified version of St. Venant's equations. So we have a continuity equation and Manning equation. This method is very simple to program, to use, and also the parameters of Manning's equation are physically based. So this is something that I want to share with you. This was a fun part of my work. That is the PC Raster. And since I'm, let's say, domain specialist, not a programmer, this tool helped me a lot to do the work on DRIHM project. And this tool allowed me to work with maps, time series very easily. So I will suggest you to Google a little bit and try to, especially if you are a Python user, you will find this tool very practical. So you can find PC Raster in two versions. I have used this one, and in that version you have a few frameworks for your work. If you want to work only with spatial processes, you can use the statical framework. If you want to work in space and time, you should use this dynamical framework, and this framework was used for this version of the HBV. This should be written stochastic, not something like that. And this is how the data could be visualized. So this is a GILA, that is a visualizing tool that is coming with PC Raster, and it's very useful. input to the HBV, the list of the input data necessary to run the HBV is fairly modest. If you choose certain time step, you need static and some of the dynamic data. For the static data, you need to have digital elevation map, land cover map, soil map. You need to have a position of rain gauges because you need to do some interpolation, and the position of hydrological station because you need to define areas that are participating in generation of the runoff. So it's very specific format of the maps is used for the HBV. Those are PC raster maps, and they can be produced and visualized with quantum GIS, with Python PC raster functions, or there is a few scripts that people from DeltaRes share with the rest of us, and you can download them and use them for the preparation of the input maps. As we speak about dynamical data for the HBV, you need precipitation, you need temperature, and you need a potential evapotranspiration. You can skip the temperature data if you don't want to model if you don't want to run the snowpack routine, but I think that you cannot calibrate the HBV model without temperature, so for the calibration, he really needs to run for a long period, so you really need temperature or you will be misled with the results. All of the input data should be put in one netcdf CF file. Here are the variables that need to be defined in this file. You can, as my colleague said, visualize them with NCView, Panoply, or some other tool for the visualization. And within the DRIHM, we needed to calculate the potential of transpiration, either for the observation or either for the output from the numerical weather prediction models. So since I had only temperature data, I decided to use Hammond's equation. So if you will run HBV, you should be aware that potential evapotranspiration is calculated on this way. Some of you ask about the calibration of hydrological models. So since the HBV is conceptual model and it has simplified equations with parameters, there is a list of the parameters that you need to set for every land use class and soil type. So you will, within the DRIHM, or if you will do that calibration manually, set the parameters, run the model, look at the results, and decide whether you want to run it again with new parameters or you are completely satisfied with the results. So the important thing is that HBV is calibrated against this discharge. So also, that is a little bit tricky with HBV. You cannot collect only series of rainfall episodes. You need to have long time series of data because you need as long as you can periods with precipitation, temperature, potential evapotranspiration, okay, we will skip it, and the discharge. You have two totally independent periods. One is for the calibration, the second one is for the verification of the model. So, but the HBV is giving much more of that, so I'm always aware of these things. I did try to model some of the catchments with shorter period of those data, but you miss most of the important things and processes. Processes are not correctly modeled. So this is the overview of the output maps. Output data are also in an NCDF CF file. And there you will find this list of the maps. You will have the information about the snowpack. You will have the information about the water and snow, the content of upper, lower reservoir, and most important, that is something that it's usually the first thing that you will visualize is surface runoff. You have also water level, and those are these output maps. Also, you can visualize them with a GILA. And this was my work with HBV within the DRIHM. It was necessary to write a few Python scripts that will transform observations or output from the NVP models to the certain desired format of the files that are necessary to run the HBV. If we have observations, we have precipitation and temperature data. They are in WaterML format. They need to be interpolated. It was used inverse distance weighting, and they were packed in the netcdf CF format. After that, there is one script that is transforming netcdf CF file to the netcdf classic file, and here the potential evapotranspiration is also calculated. So we have the desired input data, and now we can run the HBV model. Here are the, there is also one script that is transforming OR. This script is taking information about the discharge on the river, on the certain points of the river network, and pack them in WaterML format, and those data are necessary for the next model in the chain, that is hydraulic model. On the other side, if we have output from some of the numerical weather prediction models, we have a precipitation and temperature grids. We need also to interpolate those data because the grid of the NVP and hydrological model is not the same. There we also calculate the potential evapotranspiration, and now we have also the necessary data to run the HBV model. Now I will present you something that happened during the DRIHM project. We got this year one of the cases that was very severe when deep cyclone Ivković affected southern eastern parts of the Europe. Here is former Yugoslavia, Bosnia and Herzegovina, and this is Serbia. So that cyclone produced something like this. We had a lot of landslides, and most of the city that are placed along the river Sava. I think that you heard about it. It's one of the tributaries to river Danube. So there is the city of Maglaj. That was the picture from the Maglaj, and also near Belgrade we had completely flooded town of Brenovac. At the beginning, after a few days after this event, here you can see where the heaviest precipitation occurred. There are two river bases. I just put the first one. I didn't have time to put the second one. We thought that we are dealing with precipitation amount about 200 millimeters for the 3 days of this episode. But when we collected all the data, we realized that we had more than 350 millimeters of the rain for these 3 days. So we were struck with the precipitation that was 50% of our annual precipitation sum. So here you will see the scale of this flood episode. you have the animation of the flooded area. Those data are collected from MODIS. So it was huge. 62 people died. And unfortunately, this was not ready enough to be run. This is our hydro-meteorological chain within the DRIHM. So it consists of WRF NMM, rain farm, and HBV. WRF NMM was run on ECMWF boundary condition with a horizontal resolution of 4 kilometers. And I have enlarged this picture because it's clearly showing how extreme precipitation will occur if we run this model before this episode. So this is something that can say the catastrophe is coming. So we also put those precipitation predictions to the rain farm. And rain farm allow us to have an ensemble of precipitation fields with a higher spatial and temperature resolution. So the talk of Professor Scardi was completely, his talk completely assured me that this tool is very valuable if you want to see what could happen if you change precipitation in time and in place. Here are the results for the first catchment that was on the map. This is River Kolubara, and this is the output from the rain farm, and those 100 ensemble members were run, HBV was run with all of them, and here are the results. And results are clearly showing that this rainfall episode will have serious flooding consequences since the simulated discharge is exceeding any measured discharge on both rivers. This is old, only a few days. I want to show you because I never seen such a rapid flow. This is a village in eastern part of Serbia. So I was amazed when I was looking at this video. I couldn't imagine that something like that could happen. So in the DRIHM news, the latest issue, you have in detail what models we used to analyze the flood event in Serbia. It was also discussed in the DRIHM forum. And all of the things that I was spoken, or the components that you probably would like to try or to see, are on those web pages. So that's for me. I forgot to make a last slide, so thank you. Questions? Do you have any questions? Or shall we take a lunch? Okay.
I'm curious about the understanding that you have applied between war farm and rain farm.
That is the question for Nicola or Liliana.
Can you please repeat the question? Well, the understanding that you have applied between rain farm, you went from 4 kilometers to... Yes. Yes, the idea was to try to run rain farm to have a spread of possible precipitation. Even, well, we are starting 1 week before the flash floods because ECMWF was very good focused, and we had an idea that we'll have extreme precipitation, and then we are running every day work on 4 kilometers for this region. But for rain farm, I was looking only for 2 catchments. Usually well, we had a problem also with those catchments. So I was running rain pump on 500 meters horizontal resolution and 100 members of rain pump. So what Maria showed you, it was the results of 100 members of rain pump with resolution of 500 meters, but with net CDF from 4 kilometers over an hour. That was the results of our work.
That's it?